Welcome to Saxon Math, Course 3, Lesson 112, Ratios of Side Lengths of Right Triangles. Now, before we get into the lesson itself, it's important to remember that a right triangle has two acute angles and one 90-degree angle. A right triangle has one hypotenuse and two legs. Now, those two acute angles and two legs, the one 90-degree angle and one hypotenuse, kind of match up together and have a lot of really important relationships. Those relationships are part of an entire branch of mathematics called trigonometry. Now, trigonometry is the branch of mathematics that explores relationships between angles and sides of triangles. Now, there are names for each of the legs of a right triangle based off of a perspective from one of the acute angles. So, when we're going through and looking at it, we're going to have to label one angle that we're looking from the perspective of. So I'm going to say that we're looking from the perspective of this angle here. And as I'm going through these pre-examples, I'm going to continually be looking from this upper angle here. Okay? Now this is the same triangle drawn 3 times. We're looking from this angle here. Now, first thing you're going to want to know is which side's the hypotenuse. Only one of the sides is the hypotenuse, the other two are the legs. Now we can find the hypotenuse in one really simple way. The right angle is formed by the two legs, which means these two lines, which are touching the right angle, are the legs. And if these two are the legs, then the third one is the hypotenuse. And I like to say that we can know that because the right angle forms an arrow pointing at the hypotenuse. Now that means this will be your hypotenuse in all of these triangles. Right across from the right angle is still this side. Then we have two different sides, the adjacent side and the opposite side. And the adjacent side and opposite side we're saying are adjacent or opposite to this angle here. Now, the adjacent side is the one which is forming the angle with the hypotenuse. So if we look at the hypotenuse and this angle, if I make the angle marking here, the one which is forming the angle with the hypotenuse is this side. It's the one that's touching the angle. Adjacent means right next to and touching. So this is our adjacent side. So we have our hypotenuse, we have our adjacent, and then lastly, using the same angle that we used to find the adjacent, if we go across from it, and one of the ways you can find this is if you draw any line through the angle marking, it will always point at the opposite side. Okay, so that means this side is our opposite. So we have our hypotenuse, our adjacent, and our opposite. And now we have all 3 sides labeled. Now, in today's lesson, it's really important that you can first find these 3 sides. We're going to be finding the ratios between specific sides based off a certain angle. We'll be given an angle and we'll say, what's the relationship between the opposite and the hypotenuse? Or the adjacent and the hypotenuse? Or the opposite and the adjacent? Now, it's important that we are able to find the correct side in order to find the ratio, because if we use an incorrect side, we will have the incorrect ratio. We'll see what this looks like in example 1. Now, example 1 says, find the ratio of the lengths of the side opposite angle A to the length of the hypotenuse. Now, angle A is right here. So to find the side opposite of angle A, we would look across from it, and that's the side BC. In order to find the hypotenuse, remember that the right angle points at the hypotenuse, so that means that's side AB. Now, it's important to note here that the opposite and the adjacent are dependent on the angle we're talking about. In this case, the problem said angle A, but the hypotenuse is always across from the right angle, regardless of which angle you're starting off looking at. So we have BC, which the problem gave us is 3 as the opposite side, and AB, which the problem gives us is 5 as the hypotenuse. And we're asked to express the ratio of the opposite to the hypotenuse as a fraction and a decimal. Now, the opposite to the hypotenuse means opposite over hypotenuse. So we're going to put 3 over 5. Now, this is a fraction. And as a decimal, 3/5 is 0.6. So now that's a decimal and a fraction. Now, part B of example 1 asks us to use this larger triangle, which is similar to the small one over here. It's twice as big in every dimension. We can see 3 to 6, that's times 2, 4 to 8, that's times 2, and 5 to 10, that's times 2. And we can say that in this similar triangle, we're trying to find the ratio of the length of the sides opposite x. So once more, we're finding this angle here. It's the same angle that we used in part A for A, but in part B, it's called x. And we're going through our angle marking to find the opposite side, which will be side YZ. And we're comparing that to the hypotenuse. Now, the hypotenuse here, I forgot to make my angle marking for the right angle. The hypotenuse is going to be the side XY. Now, that means that for YZ, our value is 6, and for XY, our value is 10. And since we're putting the opposite over the hypotenuse, we're going to put 6 over 10 as a fraction. And if we make that a decimal, that's 0.6. And there's something really important that you should notice here. These two things, these two ratios, the opposite over the hypotenuse, are the same. And that's because within similar triangles, the ratio of the opposite and hypotenuse and the adjacent and the hypotenuse, the opposite and adjacent, the ratio between specific side lengths of that angle will always be the same. That means that since in a right triangle, you can only ever have an angle measurement in a certain set of pairs, because one of the angles is 90, so whatever angle A is, if angle X is the same, that means angle B is the same as angle Y. Because if you add this and 90 and then subtract from 180, you'd get Y. And if these two things are the same, you're going to get the same answer. So if you have a similar triangle or the same angle measurement, you will always have the same ratio. And this is the basis for how we use trigonometry in engineering and in real life, and a lesson that you'll be learning later on in this course as we get closer to the end of the year. I know we're already pretty close to the end of the year, but we're getting close to our lesson on sine, cosine, and tangent, which builds on this concept. So, something to look forward to. Example 2 says we're going to find the ratio of the side opposite angle R to the length of the side adjacent to angle R. Now, if we look at angle R, right here, the side opposite it is side ST. The adjacent side is side on the bottom, RT. Now, ST we know is 1, but we don't know RT because the problem doesn't give it to us. But it's a right triangle, so we can use the Pythagorean theorem. We can say a squared plus b squared equals c squared, where, remember, this here will have to be our c because it's the hypotenuse. It's across from the right angle. So we're going to do 1 squared plus b squared equals 2 squared. 1 times 1 is 1. B squared will stay b squared, and 2 times 2 is 4. If I subtract 1 from both sides, I'll get b squared equals 3. And then I can take the square root of both sides to get b equals the square root of 3. Which means this value is root 3. Now, if I put the opposite over adjacent, I'll have 1 over the square root of 3. Now, you might think that we're done, but there's an important concept in mathematics called rationalizing a denominator. Now, you'll be learning how to do this more in depth in lesson 120, the last lesson of this year. But there's a rule that says we can't have a radical in our final answer on the bottom of a fraction. It's just not allowed. So what we need to do is we need to think about how we can turn the square root of 3 into a whole number. And the easiest way to do that is by squaring it. In other words, multiplying by the square root of 3. But in order to keep this answer the same, we have to do that on the top and the bottom. Now, if we multiply the bottom root 3 by root 3, that's just the square root of 9, or 3. And then we have 1 times the root 3, which is root 3. Now, root 3 over root 3, the square root is now in the top. We've moved this from the bottom up to the top, and we've kept the fraction equivalent because this, root 3 over root 3, equals 1. So all we've done is we've multiplied by 1. All right, now, if you were going to try and find this as a decimal, you would need probably a calculator. If you were to plug in the square root of 3 divided by 3, then what you would get is 0.57, or about. .577. Now, that's just an approximation. If you want to go ahead and plug that into your own calculator or Google, you're free to do that. But this is the end of our lesson for today. This has been lesson 112, ratios of side lengths of right triangles. Make sure you finish up all your homework, stay safe, stay inside, and wash your hands.